Assalamu alaikum, everyone. Good evening. Ramadan Mubarak. Hope you're all doing great. So, inshallah, today I'll be talking about amino acid synthesis. MashaAllah, yani Rasul kind of explained most of the lecture. It's a simple lecture and it's really straightforward. So we just put the slides to be more appealing for you and to be smoother and easier for you just to study it, okay? And I used the same slides as the doctor's slides. I just reworded some few stuff and rearranged it in a better way, okay? So inshallah, it's not gonna take so long. And stop me whenever you have any question, okay? So let's start. Okay. So I'm just so our main objective is just one. It's the biosynthesis of the non-essential amino acids. So we will be talking about how are we going to synthesize these amino acids, okay? Now, the first slide is to differentiate between the essential and non-essential amino acid. And by now, I think your guys masters of this. When we say essential versus non-essential, we don't mean that the non-essential that we don't need them. No, both of them are needed. All the 20 amino acids are needed. However, some of them are essential to be obtained directly from the diet, okay? And the non-essential are the ones that are not going to be obtained from the diet. We're going to be synthesizing them in our body, okay? So that's the main difference. However, every rule has an exception, and the exception here is going to be, okay, so the exception here is going to be arginine. We can say that arginine is a semi-essential or conditionally essential. What do we mean by this is that it could be essential and could be non-essential. And this is mainly based on the nitrogen balance state. So nitrogen balance state, I think you guys know it. So it's whenever the depends on the protein, whether we're having more protein or we're excreting more protein, okay? So whenever we're having more protein, it's the positive nitrogen balance, and it's seen in the periods where we have growth, where we need the protein actually. For example, pregnancy, newborn, children, kids, and so on, okay? So these people might have positive nitrogen balance, and that's why basically arginine could be semi-essential, could be essential or non-essential, okay? So I think you know it, pivot Tim Hall, no need to explain it again. And yeah, guys, just know this because it will help you a lot while solving the questions, okay? Okay, so now this is the important slide. So guys, please, you have to memorize this slide, okay? Because you'll definitely 100% get a question asking you which of the following is, for example, a glucogenic and essential, which of the following is a glucogenic and ketogenic, but non-essential, okay? And it's kind of confusing a bit, so just memorizing them is easier for you and to be able to solve these questions because you're 100% gonna take it, okay? So already Rasul talked about it. Ketogenic with the mnemonic kill without the I, okay? So it's both leucine and lysine. For gluco and ketogenic, we have the non-essentials and the essentials. And the glucogenic, we have a long list. So just memorize ketogenic, glucogenic, and ketogenic, and khalas, you will be able, inshallah, to solve any question, okay? And you will see, I have a question now, and we'll try to solve it together, okay? Let's move on. Okay. So the first question, which of the following amino acids is glucogenic and ketogenic and essential? So can anyone solve this question? If you want to unmute yourself, you can unmute and solve, or if you want to type in the chat, it's fine. Okay. Okay, mashallah. Most of you guys are saying it's D. Okay. So the answer is, yeah, it's obviously D. Now let's see why is it D. So we have the first option, it's leucine, okay? Let's say leucine. Leucine, okay, yeah. Leucine, the first of all, okay, so how do we approach this question? We have glucogenic, ketogenic, and essential. So the easier thing is to see which one is essential, okay? And which one is not essential. Now, going back, leucine is essential, okay? And we have valine. Valine is also essential. Tyrosine is not essential. Tryptophan is essential. Serine is not essential. Okay. So now we have three. We have three of them are essential. Three of them are not. Two of them are not essential. Okay. Now let's move on to see which one is glucogenic, ketogenic. At the same time, it's essential. It's obviously going to be tryptophan, which is the answer D. Okay. The answer D. So moving on to talk about more about the biosynthesis of the non-essential amino acids. As we said, non-essential amino acids are the ones that are going to be synthesized, that are going to be synthesized de novo or in our body. And we have two main ways of synthesizing these amino acids. Mainly, it's going to be used by using the intermediates of metabolism. What do we mean by intermediates of metabolism? For example, an example of it is alanine, which is made from pyruvate. Okay, so pyruvate, it's an intermediate of metabolism. It's one of the end products of glycolysis and so on. This is what's meant by intermediates of metabolism. And we have alanine that's made up from pyruvate. Okay, this is an example of intermediates of metabolism. Now, the second category is the non-essential amino acids, which they are made from essential amino acids. So essential amino acid is giving us non-essential amino acid. And we have two examples of these. We'll be talking more about them in the upcoming slides. The first one is tyrosine, which is made up from phenylalanine. And the second one is cysteine, which is made up from methionine. Okay? So now here comes the interesting part. Now we'll be talking about synthesis of few amino acids, the non-essentials one, and what's the mechanism and how are you going to produce them. So this presentation, this lecture in a nutshell, it's going to be, you can summarize it in literally half an A4 page, okay, an A4 paper. How? Just know that this is going to give us this amino acids using this enzyme, and maybe it will need a cofactor, okay? So what are we going to use? What are we going to get? Which enzyme? And what are the cofactors for this enzyme? Okay, that's it. If you know this, plus this one, خلاص, inshallah, يعني you secure the lecture, okay? So now we'll start off with the first one, which is the, we have synthesis by transamination, reductive amination, amidation, serine, glycine, and the other two. Now, I just want to talk about the definition of two main things, the transamination and the amidation before we start, okay? So transamination, it's basically trans and amination. So trans, just taking or tagging an amino acid to an amino group to an amino acid, okay? So this is transamination. Amidation, it's basically by adding the addition of an amide group to an amino acid. And we'll see more about them in the upcoming slides, okay? Now, let's move on to start with the first one. So the first okay. So the first thing is going to be the transamination, the synthesis by transamination. Now, what do we mean by this is that let's take the first one as an example. Here we have pyruvate, okay? And we have pyruvate is going to give us alanine, okay, which is the non-essential amino acid. It's using an enzyme called aminotransferase, requiring the cofactor pyridoxine or vitamin B6. It's also called pyridoxal phosphate, okay? So you might have three names: pyridoxine, vitamin B6, or pyridoxal phosphate. So it's simply as we have pyruvate, we use the enzyme aminotransferase to add an amino group to pyruvate so that it becomes alanine, okay? It's as simple as this. This reaction uses vitamin B6 as a cofactor, okay? And this enzyme needs this cofactor. Now, moving on to the second one, which is the oxaloacetate, and the one that's going to give us aspartate. It uses the same enzyme using the same cofactors, okay? Lastly, the alpha-ketoglutarate uses aminotransferase to give us glutamate, okay? You're using the same cofactors as well. So here are two mnemonics, okay? So the first thing that I want to tell you about, which is, for example, if you get oxaloacetate in a question and asking you, what are you going to get? See, here we have tate and tate, okay? So can you kind of relate them together? I didn't find any other thing, okay? So oxaloacetate and the aspartate use this thing. For alpha-ketoglutarate, you have terate and tamate. It's kind of the similar thing except for the M and the R, okay? I know it sounds a bit stupid, but you can't do anything else, okay? Another mnemonic is tag a Pokemon. So let's just simplify it. T for transamination, okay? A for the enzyme aminotransferase. Then AAG, which is going to be for alanine, aspartate, and glutamate. Which is basically tag an amino acid to the pyruvate, okay, pyruvate, oxaloacetate, and alpha-ketoglutarate. So if you want to use it, use it. But for me, to be honest, I'm just going to memorize the names and not going to use any mnemonic, to be honest. Okay? This is the transamination. Second thing is going to be the reductive synthesis by reductive amination. What's reductive amination? Reductive amination is a reverse mechanism of the process that's called oxidative deamination. Okay? So this is basically what's oxidative deamination. It's happening over here. And it's going to give us one of the main things that we're going to get is ammonia. Okay? And ammonia is toxic to our body. So whenever we have an excess level of ammonia or high levels of ammonia, this ammonia will be used in order to get us a non-toxic product, which is going to be, in this case, glutamate. Okay? So for this reaction, we will be using ammonia, okay, to give us glutamate using the enzyme glutamate dehydrogenase. Okay, that's it. And here another stupid mnemonic. It's road to AAG. Road is basically reverse oxidative deamination, which is D and E, to ammonia, glutamate, and glutamate dehydrogenase. Okay, so this is the mnemonic. But again, memorize it. It's easier for you. Just ammonia. When we have high ammonia, it will give us glutamate using glutamate dehydrogenase. Okay. So now let's move on to the next checkpoint. So yeah, guys, try to solve it and let me know in the chat or in the if you want to unmute and how is it be?
Is it pyruvate for alanine and then oxaloacetate for aspartate and then alpha-ketoglutarate for glutamate?
Okay. طيب, how can we know? It's basically simply the stupid thing that I told you about. The tate for the tate, the tarate for the tamate, then alanine and pyruvate. Okay. So that's simply the question. So A to 1, pyruvate to alanine, oxaloacetate to aspartate, alpha-ketoglutarate to glutamate. Okay? Let's take a deep breath, then move on to the third one, which is going to be synthesis by amidation. Okay? So now let's talk about amidation once again. Amidation is basically the addition of an amide group. Okay? It's a carboxylic acid derivatives, which is going to replace the OH group. Okay, so the OH group is going to be replaced by an amide group, which is this one. Tamam? And what are the two main amino acids that we're gonna get? The first one is going to be glutamine. The second one is going to be asparagine. Now, here's just a diagram to simplify it. I think you don't have to know anything here. For the enzyme, the doctor didn't talk about it, so inshallah, you don't have to know it. But just know that this is this group is going to be replaced by the NH group, which is the amide, so that it gives us glutamine. Okay, this is for glutamate to glutamine, glutamate to glutamine. The second one is going to be aspartate to asparagine, and the same thing. Basically, we're replacing this group by the H2. Yeah, it's NH2, which is going to be the amide group, so that we can get asparagine. Okay, same thing for the enzyme here. I don't think that you have to know it. Just know that it's basically the replacement of this group by an amide group. Okay, and we're gonna get glutamine from glutamate and asparagine from aspartate. Tamam? So let's move on. Okay, so synthesis of serine and glycine. One thing that you have to know about this reaction mainly that it's two ways, so it's interchangeably between glycine, serine, serine, glycine. Okay, so now let's talk about the this way first, which is glycine to serine. Okay, so glycine is going to be converted to serine using an enzyme called serine hydroxy methyl transferase. Why is it called like this? Transferase because it's going to transfer hydroxy methyl group. Okay, where is it going to from where it is going to get this hydroxy methyl group? It's going to get it from the this thing N5 and 10 methyl tetrahydrofolate. It's going to act as a donor. So this guy is going to give us a methyl group. Okay, it's gonna add methyl group to glycine, so that glycine becomes serine. Okay, now this is the first thing. Glycine to serine using serine hydroxymethyl transferase, and the electron donor is going to be N5 N10 methyl tetrahydrofolate. Now let's talk about the other way around, which is going to be serine to glycine. Serine to glycine uses the enzyme serine hydroxymethyl transferase, the same enzyme, but this time serine is going to donate the methyl group. Okay, so serine donates the methyl group to an acceptor. This this dog is going to accept the methyl group, which is tetrahydrofolate, acts as an acceptor to the methyl group. This one becomes this one, and serine becomes glycine. Okay, so serine to glycine using serine hydroxymethyl transferase and using tetrahydrofolate as an acceptor. Tamam, for the methyl group. So this is basically written here. One more thing we have to note is the synthesis of serine. So we talked about synthesis of serine as from glycine, but also we have another way to synthesize serine. Okay, how? By using 3-phosphoglycerate, which is an intermediate in glycolysis. You just have to know this information. Serine could be formed by from glycine to serine, or by it's formed from 3-phosphoglycerate, which is an intermediate in glycolysis. Okay. Now here the doctor mentioned that folic acid deficiency would interfere more with synthesis of glycine. Why is this? She said because of the serine has two main ways to be synthesized, while glycine just have one way. Okay. So this is the reason that the doctor talked on. Now, the last thing, before we talk about this pathway, is there any question about the previous ones?
No, thank you.
Okay, alhamdulillah. So let's move on to talk about this one. So from methionine to homocysteine, Rasul explained, we don't have to go over it. Now we have homocysteine. Okay, this bad product. Now this homocysteine, we want to get rid of it. We can get rid of it by two main reactions. The first one is to get cysteine. Okay. Now to get cysteine, we can have from homocysteine, we should have two reactions. This is the first one, and this is the second one. Now, talking about the first one, homocysteine will be converted to cystathionine using the enzyme cystathionine synthase. Alhamdulillah, this time the enzyme's name makes sense. Cystathionine synthase to synthesize cystathionine. Okay. Now it's going to use two main things. The first thing is that it's going to use serine. Okay. So this enzyme, this reaction requires serine. Please know this. And also this enzyme requires vitamin B6 as a cofactor. Okay. Now we finish this reaction. Tamam. Now this reaction will continue to have another reaction, which is basically the conversion of cystathionine to cysteine. Okay. And this uses an enzyme called cystathionase. The doctor didn't talk about it and she didn't highlight it, so I don't think that you have to know it. Just know this this enzyme, okay? But also know that this enzyme requires vitamin B6. So vitamin B6 is needed here and here, okay? Two things. So methionine to homocysteine, this is homocysteine to cysteine. This is the reaction A to get rid of homocysteine. And we need vitamin B6, okay, to give us cysteine. Now let's move on to talk about the second reaction, which is reaction B. Okay, so reaction A gives us cysteine. Now reaction B is going to regenerate methionine again. Okay, how is this going to be? Homocysteine will be converted to methionine by the addition of a methyl group from methyl tetrahydrofolate. Okay, so do you remember the big guy, the big dog? So here it comes again. We will be using this to donate for us a methyl group. Okay, so it's going to donate a methyl group. Okay, and this is done by the by using this enzyme methionine synthase. Okay, tamam. So homocysteine, to regenerate methionine, it needs a methyl group. This methyl group is going to be donated by methyl tetrahydrofolate using the enzyme methionine synthase. And this enzyme requires a cofactor, which is vitamin B12. So now we need two main things for this reaction. We need methyl tetrahydrofolate, which is given from folic acid, and we need vitamin B12. Okay, so two main things: folic acid and folic acid for methyl tetrahydrofolate N5 and vitamin B12. Okay, to give us methionine. So let's talk about it again. Homocysteine to methionine, we need two things: folic acid, vitamin B12. Homocysteine to cysteine, we need vitamin B6. Okay. Okay, so this is written here. You can just go over it. Now we're going to be talking about the clinical significance of homocysteine. Also, Rasul elaborated on about this, and I want to talk more about it again because it's an important concept. And I think Dr. Hannah loves it because she mentioned it twice in her lecture, in this lecture and the lecture before. And it's an important thing, and they might get you questions from, so make sure to know it. You just need to know that vitamin B6 and vitamin B12 and folate are required to get rid of homocysteine, either by homocysteine to cysteine using vitamin B6 here and here, or homocysteine to methionine using folate and vitamin B12. Okay? So by this way, we can get rid of homocysteine. Whenever we have a deficiency, we might have an elevation of homocysteine, and homocysteine is not a good product for the heart. Okay, it could result in some heart diseases, some vascular diseases, and so on. So this is basically what's written here. We need folic acid, we need vitamin B12, we need vitamin B6. Could be called pyridoxal phosphate, could be called pyridoxine. Okay. This slide is just explaining to you what could happen if we have an elevated homocysteine. Homocysteine will result basically in a reaction called homocysteinylation, which is the formation of the disulfide linkage between the proteins and the homocysteine. And this will give us this product. And obviously this product is a cytotoxic, which means that it's toxic to the cells. It could result in cellular toxicity and damage whether to the heart, to the vessels, and so on. Okay? Atherogenesis is the formation of somehow like plaques or clots in the vessels. So just know this. And lastly, now spina bifida. Spina bifida, I think you guys know it from MSK. Spina bifida is just whenever we have a defect in the formation of the back, simply the back. And it's mainly happening because of folic acid deficiency during pregnancy. So always they advise pregnant women to take folic acid supplements to prevent congenital diseases, for example, to prevent spina bifida. And it could happen whenever we have also elevated homocysteine, okay? Because obviously folic acid deficiency could result in elevation of homocysteine. Tamam? Now this is the last reaction. Last reaction is basically involving the synthesis of tyrosine from an amino acid. Okay, so I gave you this as an example before when we talked about the synthesis of the non-essential amino acids from another amino acid. This is basically by using phenylalanine to give us tyrosine, and this requires an enzyme called phenylalanine hydroxylase. What does it mean from its name? It's basically the addition of a hydroxyl group to phenylalanine to become tyrosine. And this enzyme requires two things. The first thing is that it requires O2, okay? And the second thing that it requires this thing. This is called tetrahydrobiopterin, or THB, or BH4, okay? So we need it as a cofactor for this enzyme. So just to recap it, phenylalanine going to give us tyrosine using phenylalanine hydroxylase, requiring 2 cofactors, tetrahydrobiopterin and O2. Okay? Okay, done. Any questions before moving on to the questions? It's a really simple lecture. Inshallah, just memorize it and it's fine. Okay, so let's move on to questions. So I would like someone to, if they can unmute and answer it, or just in the chat, please. So whoever said that it's B, the answer is yes, it's B. Because can you tell me, okay, so can you tell me what's the name of the reaction that's going to give us this glutamate from ammonia? Just to make sure that everyone knows it by now. Reductive amination, okay, nice. So it's the reductive amination or the reverse of oxidative deamination, okay? So what's happening here is that, okay, so this is the 2 main sentences. Then, which of the following amino acids can covalently bind ammonia and store it in a non-toxic form? So this question is addressing the concept that whenever we have an excess and high levels of ammonia, ammonia will be converted to glutamate in the reaction called reverse of oxidative deamination. Okay, and this will use an enzyme, which is the next question. What's the answer? Yes, exactly. So the answer is D. It's glutamate dehydrogenase. So glutamate dehydrogenase converts the ammonia into and gives us glutamate. Okay. So just to sum it up, we have 2 main concepts from this lecture. The first one is that you have to know which one is ketogenic, which one is glucogenic, and which one is both, and essential and non-essential, obviously. This is the first thing. The second thing is that know the thing that we'll be using, the enzyme, what is going to give, and the cofactors, and that's it. Okay. Any questions?
No, thank you so much.
You're welcome. You're welcome. You're welcome. Okay, so okay. So my contact is in the first slide here. If you have any questions, just you can email me or you can just send me a message or whatever. Okay. So inshallah, hopefully it was helpful. And plus, if you don't have any question, it's fine. You can stop the recording, Zahra. Thank you.